JUnit 3.8.x pattern summary in JUnit. Here you can see JUnit 3.8.x patterns summary. Uh, the goals of JUnit. What are the goals of JUnit? First, we have to get back to assumptions of development. If a program feature lacks of automated test, we assume it doesn't work. This seems much safer than prevailing assumption that if a developer assures us a program feature works, then it works now and forever. From this perspective, developers aren't done when they write and debug code. They must also write tests that demonstrate that the program works. However, everybody is too busy. They have too much to do. They don't have enough time to screw around with testing. So the number one goal is to write a framework within which we have some glimmer of hope that developers will actually write tests. The framework has to use familiar tools, so there is little new to learn. It has to require no more work than absolutely necessary to write a new test. It has to eliminate duplicated effort. If this was all test had to do, you would be done just by writing expressions in a debugger. However, this isn't sufficient for testing. Telling me that your program works now doesn't help me, because it doesn't assume me that your program will work 1 minute from now after I integrate, and it doesn't assure me that your program will still work in 5 years when you are long gone. So the second goal of testing is creating tests that retain their value over time. Someone other than the original author has to be able to execute the test and interpret the result. It should be possible to combine tests from various authors and run them together without fear of interference. Finally, it has to be possible to leverage existing tests to create new ones. Creating a setup or fixture is expensive, and a framework has to enable reusing features to run different tests. The design of JUnit will be presented in a style first used in. The idea to explain the design of a system by starting with nothing and applying patterns one after another until you have the architecture of the system. We will present the architectural problem to be solved, summarize the pattern that solved it, and then show how the patterns was applied to JUnit. Test case. First, we have to make an object to represent our basic concept, the test case. Developers often have test cases in mind, but they realize them in many different ways. Print statements, debugger expressions, test scripts. If we want to make manipulating test easy, we have to make them objects. This takes a test that was only implicit in the developer's mind and make it concrete, supporting our goals of creating tests that retain their value over time. At the same time, the object developers are used to well developing with objects, so the decision to make test into object supports our goal of making test writing more inviting, or at least less imposing. The command pattern fits our needs more nicely. Quoting from the intent encapsulate a request as an object, thereby letting you queue or log request. Commands tell us to create an object for an operation and give it a method to execute. To illustrate the evolution of JUnit, we use diagrams that show snapshot of the architecture. And because we expect this class to be reused through inheritance, we declare it a public abstract. For now, ignore the fact that it implements the test interface. For the purpose of our current design here, you can think of test case as a long class. For every test case is created with a name, so it a test fails, you can identify which test fails. The notion we use is simple. It annotates classes with shaded boxes containing the associated pattern. When the role of the class is in the pattern, it is obvious, then only the pattern name is shown. If the role isn't clear, then the shaded box is augmented by the name of the particular participant this class responded to. This notation minimizes the clutter in diagram and was first shown in here. This shows this notation applied to here to test case. Blanks to fill in and run. The next problem to solve is giving the developer convenient place to put their fixture code and their test code. The declaration of test case as an abstract says that the developer is expected to reuse the test class by subclassing. However, if all we could do was to provide the superclass with one variable and no behavior, we wouldn't be doing much to satisfy our first goal, making test easier to write. Fortunately, there is a common structure to all tests. They set up a test fixture, run some code against the fixture, check some results, and then clean up the fixture. This means that each test will run with a fresh fixture, and the results of one test can't influence the result of another. This supports the goal of maximizing the value of the tests. Template method addresses our problem quite nicely. Quoting from the intent, define the skeleton of an algorithm in an operation, differing some steps to subclasses. Template method lets subclass redefine certain step to an algorithm without changing the algorithm's structure. This exactly right. We want the developer to be able to separately consider how to write the fixture, setup and tear down code, and how to write the testing code. The execution of this sequence, however, will remain the same for all tests, no matter how the fixer code is written or how the testing code is written. The default implementation of these methods method do nothing. Since setup and tear down are intended to be overridden but will be called by the framework, we declare them as protected. The second snapshot, here you can see the template method here. The template, reporting test result. If the test case runs in a forecast, does anyone care about the result? Sure, you run the test to make sure they run. After the test has run, you want a record, a summary of what did and what didn't work. If test had equal chances of succeeding or failing, or if we only ever ran the one test, we could just set a flag in the test case object and go look at the flag when the test completed. However, tests are intended to be highly asymmetric. They usually work. Therefore, we only want to record the failures and a highly condensed summary of the success. The Smalltalk best practice patterns has a pattern that is applicable. It is called collecting parameter. It suggests that when you need to collect results over several methods, you should add a parameter to the method and pass an object that will collect the result for you. We create a new object, test result, to collect the result of running test. This simple version of test result only counts the number of tests run. To use it, we have to add a parameter to the test case.run method and notify the test result that the test is running. And the test result has to keep track of the number of tests to run. We declare the test result method start test as synchronized so that the single test run can collect the result safely when the tests are run in a different threads. Finally, we want to retain a simple external interface of test case. So we create a no parameter version of run that create its own test result. If tests always run correctly, then we wouldn't have to write them. Tests are interesting when they fail, especially if we didn't expect them to fail. What's more, tests can fail in ways that we expect. For example, by computing an incorrect result, or they can fail in more spectacular ways, for example by writing outside of bound of an array. No matter how the test fails, we want to execute the follow test. JUnit distinguishes from failures and errors. Possibility of a failure is anticipated and checked for with assertions. Errors are anticipated problems like an array index out of bound exception. Failures are signals with an assertion failed error to uh, distinguish and yeah. JUnit comes with a different implementation of test result. The default implementation counts the number of failures and errors and collects the results. The text result collects the results and present them in a textual form. Finally, the UI test UI test result is used by the graphical version of JUnit test runner to update the graphical test status. The test results is an extension point of the framework. Client can define their own custom test classes. For example, an HTML test result reports the result as an HTML document. Now stupid subclasses test case again. We have applied command to represent a test. Command relies on a single method like execute called run in the test case to invoke it. The simple interface allows us to invoke different implementation of a command through the same interface. We need an interface to generally run our test. However, all test cases are implemented as a different method in the same class. This avoids the unnecessary proliferation of classes. A given test case class may implement many different methods, each defining a single test case. Each test case has a descriptive name like test money equals or test money add. The test cases don't conform to a simple command interface. Different instances of the same command class need to be invoked with a different methods. Therefore, our next problem is to make all test cases look the same from the point of view of the invoker of the test. Reviewing the problems addressed by the available design patterns, the adapter pattern springs to mind. Adapter has the following intent: convert the interface of the class into another interface clients expect. This sounds like a good match. Adapter tells us different ways to do this. One of them is a class adapter, which uses subclassing to adapt the interface. For example, to add test money equals to run test. We implement the subclass of money test and override the run test to invoke test money equals. To use the subclassing requires us to implement the subclass for each test case. We put an additional burden on the tester. This is against the JUnit goal that the framework should make it as simple as possible to add the test case. In addition, creating a subclass for each testing method result a class bloat. Many classes with only a single method are not worth their cost, and it will be difficult to come up with the meaningful names. Java provide anonymous inner classes which provide an interesting Java specific solution to the class naming problem. With anonymous inner classes, we can create an adapter without having to invent a class name. This is much more convenient than full subclassing. It prevents compile time type checking that at the cost of burden on the developer. Smalltalk best practice patterns describe another solution for the problem of different instances having differently under common heading or pluggable behavior. This idea is to use a single class which can be parameterized to perform single different logic without requiring subclassing. The simple form of pluggable behavior is the pluggable selector. Pluggable selector stores a Smalltalk method selector in an instance variable. This idea is to limit is not limited to Smalltalk. This is also applicable to Java. In Java, there is no notion of method selector. However, the Java reflection API allows us to invoke a method from a string representing method name. We can use this feature to implement a pluggable selector in Java. As an aside, we usually don't use reflection in ordinary application code. In our case, we are dealing with an infrastructure framework, and it is therefore okay to wear the reflection hat. JUnit offers the client the choice of using pluggable selector or implementing an anonymous adapter class also. To do so, we provide the pluggable selector as an default implementation of run method, run test method. In this case, the name of the test case has to correspond to the name of the test method. We use reflection to invoke the method, and first we look up the method object. Once we have the method object, we can invoke it and pass it to argument. JDK 1.1 reflection API only allows us to find public method. For this reason, you have to declare test methods as public, otherwise you will get no such method exception. Don't care about one or many test suite. To get confidence in the state of a system, we need to run many tests. Up to this point, JUnit can run a single test case and report the result in a test result. Our next challenge is to extend it so that it can run many different tests. This problem can be solved easily when the invoker of the test doesn't have to care about whether it runs one or many test cases. The popular pattern to pull out in such situation is composite. To quote this intent composite objects into a tree structure to represent part whole hierarchies. Composite lets client treat individual objects and compositions of object uniformly. The point about part whole hierarchies is of interest here. We want to support suits of test. Composite introduces the following participant component. Declares the interface we want to use to interact with our tests. Composite implements this interface and maintains the collection of tests. Leaf represent test case in a composition that conforms to the component interface. The pattern tells us to introduce an abstract class which defines the common interface for a single and composite object. The primary purpose of the class is to define an interface. When applying composite in Java, we prefer to define an interface, not an abstract class. Using an interface, avoid committing JUnit to a specific base class for tests. To all that is required is that the test conform to this interface. Test case corresponds to a leaf in a composite and implements the interface as we have seen above here. Next, we introduce the composite participant. We name this class test suite. A test suite keeps its child test in a vector. The run method delegates to its children. Finally, the client have to be able to add test to the to a suite. They can do so with the method add test. Notice how all of the these things only depends on the test interface. Since both test case and test suite conforms to the test interface, we can recursively compose suites of test suites. All developers can create their own test suites. We can run them all by creating test suites composed of those suites. This works fine, but requires to add all the tests to a suite manually. Early adapters of JUnit told us this was stupid. However, you can write a new test case. You have to remember to add it to a static suite method. Otherwise, it will not be run. We added a convenient constructor to test suite which make the test case class as an argument. Its purpose is to extract the test methods and create a suite containing them. Test methods must follow the simple conventions. They start with the prefix test and take no arguments. The convenience constructor uses this convention, constructing a test object by using reflection to find the testing method. The original way is still useful when you want to run subset of test cases only. So here we are at the end of this JUnit tour with JUnit 3.8.x. This figure shows the design of JUnit at a glance, explained with patterns here. Notice how test case, the central abstraction of in the framework is involved in 4 patterns. The pictures of mature object design shows this same pattern density. The star of this design has a rich set of relationships with the supporting players. Here you can see the test interface here. It's a composite component here. Here you can see 2 subclasses. This test case and test suits is inherited from test. Test case has command pattern, template pattern, and composite leaf here, and pluggable selector. And test suit has a composite, and it has run method and add test method. Test suit composite of tests. Test case has run method, run test, setup, and tear down, and pluggable selector fname. Test case is connected to test result. Here it has a collecting parameter pattern, and this one is inherited from test case, and it has this class. This follows the adapter pattern. It has run test method. Now this is the end of my presentation. Thank you very much for watching it.